Have you ever wondered where the color of flowers comes from? Where those blues come from? Where those pinks come from? And all that sort of thing? Well, a significant part of the answer lies in the characteristics of the soil that these plants grow in. The chemistry of the soil, its structure, and those kinds of factors. And that is what we are going to be considering today, finishing up the topic of the nature of soil. Now, most people, when they hear the term soil, think that this has got to be a pretty deadly topic. But I have to tell you, of all the courses that I took during my time in college, the one that I found most interesting of all was my course in soils. It provided a lot of the answers that I needed to explain how the natural world worked. It gave me great insights into plant distributions, causes for the development of plant communities, and a lot of the other topics that are going to be covered in the next unit that we're going to do. Once you understand plants, then you can also understand animals also. So it really is a foundational kind of a topic that it is well worth our while to understand a bit about. So let's begin our discussion at the beginning, where soil comes from. What we're looking at here is the Natchaug River as it flows through northeastern Connecticut. It flows in this particular area through bedrock. The rocks that you're looking at here are the types of rocks that we refer to as gneisses, if you remember from our last program, spelled G-N-E-I-S-S. Very widespread type of rock that occurs in much of the Northeast. Now, over time, this rock gets weathered by things like water action. You can see that the surfaces of those rocks are smooth. They've been getting smooth for a long time. A lot of the smoothing you see here happened during Ice Age times, when this area would have been under a good 5,000 feet of ice. And as that ice melted, all the debris coming down the river would have abraded the surfaces. The water itself would have had chemical interaction with the rocks. And so this bedrock that you see here is getting eroded into its component particles, that stuff we call sediment. Now here's a different view of a similar sort of phenomenon going on at a different location. This is a small scale view of bedrock as it occurs on a high mountain peak in the Berkshire Mountains, right on the Connecticut-Massachusetts border. We're looking down at a few very small plants that are growing out of this bedrock. These are plants referred to as potentillas. It's a particular species called Potentilla tridentata, which is an Arctic alpine plant for all intents and purposes, but on the most extreme environments in the Appalachians, of which the Berkshire Mountains are a part, you can find these plants growing there on these highest elevations where conditions simulate to a certain degree Arctic kinds of conditions. Now, if you look carefully at some of the stuff underlying these plants, you'll notice that there are also some other kind of pale green and pale gray things on the surface of the rock. Those are lichens. In the upper left-hand corner, there's some deeper green stuff. That's some species of moss. So what you're looking at here is a community of organisms which is assisting with the process of breaking down this rock. The rock itself is being weathered by rain, but it's also being acted upon chemically by the kinds of organic acids that these plants produce. And so the combination of all these factors is breaking down this rock, and the breakdown products are accumulating in the crevices. So we have soil developing, and soil is not simply mineral in constitution. It also consists of a organic component, the dead plant remains from these organisms that are attempting to make a living there. So let's focus in on the surface of the soil a little bit further. We're looking here at the trunk of a big-tooth aspen, which, by the way, is a rather commercially important species. It's harvested for very fine quality interior carpentry kinds of lumber. It has very tight grain. It's sold under the name of poplar. But the real topic of this slide is what the tree is growing in the soil. Notice all those dead leaves on the surface. Well, those dead leaves, over time, decay as a consequence of action by soil organisms, by bacteria, by fungi, and that stuff, those decayed plant remains, all those dead leaves, get mixed into the upper layer of the soil. As I said, soil is not simply a mineral substance, it is also comprised in part of organic matter, the dead remains primarily of plants. So let's summarize a bit. The properties that soil inherits is primarily from the inorganic parent material, the rocks, by and large, from which the soil is derived. But over time, we can expect that the living environment is going to interact with that mineral environment and insert various classes of organic matter into the soil, especially in the upper layers. If you look at the very upper part of the photo in this picture here, you can see that it is darker brown than the underlying material, which, by the way, is mostly glacial sand and gravel. This is a road cut, or actually it's a cliff face, from Block Island, Rhode Island again, that place which is at the terminal moraine of the last glaciation, the Wisconsin Glacier. And in the intervening 10,000 or so years since the end of glacial times, organic material has gotten incorporated into that upper layer. A related issue to that of the physical properties of soils is that of the horizons of soil, the layering of soil that can be seen when one makes a pit in the soil, or when one sees a road cut or a cliff face or something like that. The uppermost layer of the soil, that which is principally organic matter, is called the O horizon. The next layer of soil, commonly referred to as topsoil, is that of mineral soil into which a significant amount of organic matter has been included. Another layer, called the E layer, can be found in areas where soil undergoes a lot of leaching, so that various sorts of substances in the soil get leached out of it into the next layer, which is the B layer. And that is the zone of accumulation of some of those materials like silica and clay and iron and aluminum. The stuff that underlays all this is called the parent material, which is largely chemically unchanged from its original state, and it consists of primarily unconsolidated material. The deepest layer of all is the bedrock. Now let's turn our attention to soil texture. That is the size of the particles that make up soil. Now we're looking here again at Block Island, Rhode Island. We're looking at a beach below the cliffs that shows a full range of soil particle sizes, from the giant boulders in the foreground. And of course boulders are not soil, but they eventually will weather into soil. Do notice, however, how rounded those boulders are. That's a consequence of glacial activity to a significant degree. Those boulders have gotten rolled around in ice for a very long time. So we have those, and next to them we see various classes of smaller rocks that we usually refer to as cobbles. And interspersed among the cobbles we have tinier kinds of pebbles that we might call gravel. And then a little bit back from that, we're looking at sand of various sizes, everything from coarse to fine sand I think we could likely find in that little section of beach. But then as we look way in the background, notice that there's a darker grayer area on the cliffs. Well, that darker grayer area is of another kind of soil particle that we call clay, the tiniest of the soil particles. That deposit of clay is associated with a much, much earlier glacial event, it is thought. But it is a widespread clay deposit in this part of the world. Clay in many of the soils of the Northeast is not a very important component, but in this particular area it's quite widespread. We often think of clay as more associated with volcanic soils. And you can usually tell if you're in a volcanic clay-rich soil because the soil is sticky. We can also find clays accumulating along rivers in our area here in the Northeast, however. And there is one other soil particle size that we really can't see specifically in this picture, but it's something in between the clays and the sand you're looking at. Particles referred to as silt, which are kind of in between size. Here's a closer up view of those clays. You can see how dark gray they are in comparison to the pale colors of the surrounding primarily sandy gravelly soil. Now, I know we've already seen this slide, but I thought it was worth bringing it back just briefly to remind us of the relationship of the various classes of soil particle sizes, from the largest coarse sand to the tiniest clay. Now, here's a slide from the Natural Resource Conservation Service, formerly known as the U.S. Soil Conservation Service. My old employer, in fact. U.S. Soil Conservation Service, back when I worked for them, had the reputation of being one of the best and most professional agencies in the federal government. Certainly during my time, that was my experience. People who worked there were most impressive in their knowledge of soil and in their ability to give farmers and homeowners expert advice on how to use the characteristics of their soil to best advantage. Now notice the triangle in the graph on this slide. The purpose of the triangle is to separate the three main textural classes of soil: sand, silt, and clay. And we can use this triangle to define the USDA textural system of soil, USDA standing for United States Department of Agriculture. So in the upper part of the triangle, we have soils that predominate in a clay component of them. In the lower right, we have soils that are heavy in silt and lower in clay and sand. And in the lower left, we have soils that are primarily composed of sands with smaller amounts of clay and silt. Now here in New England, our soils most typically fall into that classification called sandy loams. Many of our soils around here are in that category. And some of them actually are fairly good soils for certain types of agriculture, although more typically our New England soils are not the greatest agricultural soils. Having some clay component is very important in a variety of ways in terms of soil quality, and we'll be looking at some of those as we look at some of the upcoming photos and slides. So it's again time to summarize. So texture of a soil depends on particle size, and the particle sizes are the sands and the silts and the clays. And so soils with differing textures have differing physical and chemical properties. Hence, these properties influence growth of plants within them differently. Let's turn our attention back to the question of how is it that different flowers get to be different colors? In this context, let's consider the nature of plant nutrients. This plant, by the way, is columbine, and notice how it's growing right out of a rock. And notice also that the rock is covered in mosses and lichens. And again, this raises that earlier issue I brought up of how it is that living organisms are actually part of the process of breaking down rocks. This columbine is growing not really in the rock itself, but in a little pocket of soil that's accumulated in a crevice in a rock. A crevice that is the consequence of repeated freezing and thawing and cracking of the rock and processes like that. And then in this crack, over time, as this rock has weathered and as wind has blown materials, we've had a little bit of soil accumulate there. And so this soil has particular kinds of chemical characteristics that allow this plant to produce these red and yellow flowers. Here are the two principal classes of soil nutrients. The major class would be the macronutrients, those chemicals that plants need in large quantities, notably potassium, magnesium, calcium, nitrogen, phosphorus, and sulfur. Micronutrients are not to be underestimated, however. They are not needed in large quantities, but their influence on how plants work is critical. Things like iron and manganese and zinc and copper and chlorine, boron, molybdenum, sodium, all these kinds of chemicals are involved in specific physiological pathways in plants, and so their presence is critical. Now, to be sure, different plants require different quantities of micronutrients, but micronutrients as a class is something that is very important to the growth of plants, and including things like the color of flowers in many instances. Here is a little sampler of some of the sorts of things that these soil nutrients do. Some serve as catalysts for chemical reactions. Some are important in the electron transport system that hopefully you remember from introductory biology. Things like iron, for example. Some serve as structural components of molecules. So, for example, Calcium is a constituent of the cell wall of plants. That's probably another fact that you've encountered previously. Some, again, in this case the ion calcium is involved in things like permeability of cell membranes. We're looking here at a shovel full of floodplain soil. Notice that it's rather dark, rich in organic matter, among other things. Tends to be a nutrient-rich and good agricultural soil when it's managed properly. Now, it is one thing for plants to require nutrients that are in the soil, but it is quite another issue for plants to be able to get it away from that soil. That is the issue of cation exchange. Keep in mind that many of these things that plants need are positively charged ions, cations. And so let's consider in a little bit more detail the capacity for soils to give up these nutrients. So again, cations are positively charged ions. Things like potassium, calcium, sodium are among some of the important chemicals that plants use, as we've seen. And so cation exchange capacity specifically refers to the soil's ability to hold these nutrients and give them up to plants. Now, among the soil textures, those that have the best capacity for holding on to cations are silts and especially clays, because of the details of the structure of clays. They are very good at holding on to these positively charged materials. So they're referred to as having higher cation exchange capacity. Sands, on the other hand, tend to be rather poor at doing that. They don't have the chemical ability to attach to positive ions. Let's go back to our floodplain soil and examine it a little bit more carefully. By floodplain, by the way, I mean those areas along rivers that periodically flood, usually in the springtime with spring meltwaters from the north. We'll discuss floodplains in greater detail later. What we're looking at here is a soil pit that I've dug into this floodplain soil. If you look at the uppermost horizon in that pit, you can see kind of orangey, rusty looking material. And you can see it also to the left of the pit where I've deposited some of that upper layer of soil. Well, the reason for that orangey, rusty color is because of the presence of iron in the soil. This particular iron has been reduced, and if you remember oxidation reduction reactions, the iron is reduced because it has gained electrons. Notice also at that upper horizon in the soil pit, there's some gray areas interspersed with the reds. That is referred to as mottling. And this reduced iron and mottled soil are characteristic of floodplains. Floodplain soils tend to be rather waterlogged for much of the year. And in that kind of a situation, there's not a whole lot of oxygen aerating that soil. And so these kinds of processes occur in waterlogged soils. It is a sign, in fact, to people who are thinking about building a house somewhere. If they see this sort of thing, it means that it's probably not a good place to be constructing. So this brings up the topic of soil water. Now, these soil particles have got little spaces between them, and those spaces are called pores. In soils with large pores, like sands, such as dune sands like you see in the upper photo here, these drain water rather rapidly because they don't have a good hold on the water between those pores. It results in sandy kinds of soils being prone to dryness. In contrast, soil with small pores, especially clay soils, these hold water very tightly and can become waterlogged in situations like you see in the lower photograph, areas along rivers. This is a floodplain marsh you're looking at, and that soil that underlays that is wet for most of the year. Clay has the chemical capacity actually to hold water so tightly that not all of it is actually available to plants. This chemical bond between the water molecules and the clay molecules is strong enough to overcome the force of pulling by the plant's roots on that water. Now, there are a few terms related to soil water that it's worth knowing about. One is field capacity. These are agricultural kinds of terms. Field capacity refers to the amount of water the soil can retain against the action of gravity. So when a soil is moist, when it's got a certain amount of water in the pores, that will stay there even against the force of gravity acting on it. There's enough electrical attraction between the soil particles and the waters that it stays put. The wilting point of water is another term that's worth mentioning. When there is not enough water in the soil for plants to maintain their turgor pressure, the pressure that inflates their leaves, then the leaves are going to start wilting. And so there needs to be enough water in the soil in order to avoid that wilting point from being reached. Remember, during the growing season, plants are actively transpiring. They're pulling up water and they're losing some of that as water vapor. So there needs to be a sufficient supply of water in the soil to account for that. Now, soil water is a big issue in agriculture, not surprisingly. So there are a variety of federal agencies that keep track of these sorts of things. And what you're looking at here is a sequence of maps of the United States during different months that are examining the droughtiness of soils across the country. Our last topic under the heading of soils is that of soil taxonomy, the major types of soils that are recognized to exist around the world. And they are of these groups that you see here. There are the spodosols that develop in colder climates, in the boreal zone. So in places like Canada, they tend to be acidic and nutrient poor. And then there are the alpha sols that develop in temperate climates under deciduous forests. So much of the northeastern United States and southeastern parts of Canada have these kinds of soils. And these soils maintain nutrients much better by the recycling of leaf litter, like you're looking at in the background of this picture here. The mollisols are soils that develop in drier areas, so like in the midwestern part of the United States. They are among the best agricultural soils on the continent of North America. They're high in organic matter and in nutrients because the precipitation is insufficient for leaching those nutrients out of the soil. Another class of soils are the aridosols, which develop in arid regions, not surprisingly from that name. So precipitation is, again, insufficient for nutrient leaching, kinds of soils that you might find in the southwestern parts of North America. Oxisols develop in wet tropical regions, places that would be vegetated by rainforests. So a good portion of northern South America, for example, would have these. Surprisingly, although they are growing rainforest, they do tend to be nutrient poor and with little organic matter. What goes on is that any nutrients that are present are rapidly recycled through these systems through rapid decomposition of leaf litter and any other kinds of organic matter. It's rapidly recycled back to the plants again. And that, as we'll see when we talk about subjects like this later, is why cutting down rainforests can be very problematic, because it can then become very difficult to grow forest back there as all those nutrients are lost from the system. So let's look at a map of this. So here's the United States and a map prepared by U.S. Soil Conservation Service, Natural Resource Conservation Service now, in which the major soil groupings, which are called soil orders, by the way, are illustrated. Let's look at one individual one. If we just look at the alpha sols, then you see this kind of a distribution across the United States. And notice that within this soil order there are suborders. On the right-hand side of the image, you can also see what an alpha sol would look like if one did a soil profile in a region in which these soils were present. One last U.S. Department of Agriculture map shows the distribution of these major soil groupings around the entire world. Now, if you look carefully at the legend on the lower left, you'll notice that there are several additional soil groupings that I did not specifically define in my earlier slide. This is a more complete accounting of the major soil orders of the world. And with that, we have reached the end of the topic of soils and the end of our first major subject, Earth systems and resources. And so we will pick up next time discussing the living world.